So did anybody actually try the problem from this morning? Probably nobody had much time for it, but so just to remind you, the problem was you have the sun, you have the Earth going around the sun, and we said, okay, what if the sun suddenly loses, let's say through a Mach supernova explosion, a fraction of the mass? How much mass would the sun need to lose in order to unbind the Earth? Okay, so the answer in this case is fairly simple. I intentionally picked sort of a simple problem where you have all of the mass sitting just in one of the objects. The mass ratio is 1,000,000 to 1, so you can assume that the sun is not moving, only the Earth is moving around the sun. And in this case, the total energy of the system before any explosion is E initial is minus G M sun, M Earth, let's write it like this, divided by their separation between the Earth and the sun. Okay, that's a potential energy. Of course, there's a kinetic energy, which is half of that value by the virial theorem. If the sun explodes, the Earth doesn't know about it. It's an instantaneous explosion. The Earth just keeps moving at the same velocity, right? It doesn't know any better. So the kinetic energy of the Earth stays the same. So the question is, what happens to the potential energy? Well, all we're changing instantaneously, again, the separation doesn't change. All we can instantaneously change is the mass of the sun. And the system is unbound when the total energy becomes positive rather than negative. So for the system to become unbound, this term has to be not minus gm sun m Earth over A, but the moment this goes to minus gm sun m Earth over 2A, the total energy is now 0, and the Earth is unbound. So that means if the mass of the sun goes down by a factor of 2, from m sun to m sun over 2, the binary is unbound. Okay, this was a simple example where one of the objects had all of the mass, but actually it turns out, if you do this a little bit more carefully, which I won't waste your time on, it doesn't matter how you lose the mass, or whether all of the objects, one of the objects has all of the mass, or the mass is shared equally between the objects. If you lose instantaneously half the mass of the binary, the entire system is unbound. So first of all, that's actually an important point to remember. If during a supernova you lose half the mass, it doesn't even matter whether you have a kick or not, the binary is unbound. So for instance, if you think of a binary which has a neutron star, and the second companion is, let's say, a 5 solar mass helium star, and you imagine it collapses into a neutron star, so you go from a total mass of 1.4 solar masses plus 5 solar masses, and let's imagine this were to collapse all the way into a neutron star, losing 3.6 solar masses of energy. So suppose this went to 1.4 solar mass plus 1.4 solar mass system. You went from a total mass of 6.4 solar masses to a total mass of 2.8 solar masses. You've lost more than half of the mass in a supernova explosion. You don't have a binary anymore. You don't need a supernova kick. You don't need any asymmetry. Even if it's a perfectly symmetric supernova explosion, your binary has been unbound, right? So no more gravitational waves from a neutron star merger, right? So this is already an interesting constraint. But of course, you don't necessarily need the binary to be completely unbound, even if you only lose a fraction of the total mass, less than half of the mass. Okay, you can imagine, of course, binaries, if you really drop the mass by a factor of 2, you go to sort of a parabolic orbit, right? Energy equals 0 orbit. If you go to an orbit suddenly, which, yes, it's still bound, but it only has a small fraction of the initial energy, that means you have to increase the apoapsis distance significantly, because the total energy sets for a given mass sets the semi-major axis, right? The energy is just inversely proportional to the semi-major axis. So, but of course, the periapsis stays the same, the semi-major axis gets much larger, so your binary becomes much more eccentric. And so in general, if you just lose a significant fraction of the mass instantaneously, you end up moving to a very eccentric binary, and this is something called the Blau kick, because a Dutch astronomer named Blau wrote a couple of papers about this around 1960 or late 1950s. But the basic idea is this might be one of the reasons why some of the double neutron star systems we observe, for example, have significant eccentricities. So, as I mentioned this morning, the Hals-Taylor binary, pulsar 1913 plus 16, has an eccentricity in excess of 0.6. And of course, it could be that it got a favorable kick, right? If during a supernova you get a kick in the same direction as the direction of motion, you tend to increase the eccentricity of the binary and increase the same major axis as well. So maybe that's what happened. But it could also be that even without much of an asymmetry, you would just naturally from the instantaneous mass loss end up with this highly eccentric binary. The last thing to mention, by the way, is that even if the mass loss is gradual, for example through winds, you will tend to widen the binary. So you can take the limit where instead of losing a very similar kind of calculation, I'm not going to repeat it for this in the interest of time, but you can take a limit to a case where you're losing only a very small fraction of the mass, and because you're losing a small fraction of the mass, you can average things over the orbit, so you're not giving the binary any eccentricity, you're losing just as much mass during this phase of the orbit as during this phase of the orbit, so the eccentricity doesn't change, but you're still widening the binary, you're still decreasing increasing, making less negative the total energy, so the same major axis is going up, and in fact you find that if you have a case of gradual mass loss, then dA over A is something like minus dm over m, where this is actually the total mass now. So if you're losing total mass, so dm is negative, m is the total mass of the binary. So dm is negative when you're losing total mass. If I'm losing total mass, then I'm increasing in my separation of the binary. So for every factor of 2 drop in the mass, I'm increasing my overall binary separation by a factor of 2. So winds tend to widen binaries, right? Mass loss through stellar winds widens binaries. Okay, so now let's return to our model. And the model we were talking about was this isolated binary evolution through a common envelope phase. So again, we said we want 2 massive stars, sufficiently massive to make black holes, let's say, if we want to make binary black holes this way. We want the 2 stars to be far enough apart that they don't just merge, because that's not interesting for us. We want each of them to be massive enough to make a black hole. We want the first episode of mass transfer to be stable, so we don't want a mass ratio that's too extreme. So when this star expands at the end of its main sequence, turns into a giant, overflows its Roche lobe, transfers of mass to the companion, we are assuming that this is going to be a stable mass transfer. This mass transfer may be fairly conservative. How conservative it is depends in part on the let's say state of the accretor relative to the state of the donor. So at least, let's say, different people model this in different ways. We don't actually know what the ground truth is, so this is partly based on simulations and models. So we have a population synthesis code called COMPASS that my group has written. So COMPASS is so population synthesis is basically an idea that says, look, evolving individual binaries, you can try to do this in detail using codes like MESA, for example, which try to do full, careful stellar evolution, at least in 1D. People have also tried to do this in 3D with hydro simulations, but that's very, very computationally expensive. If you do this in 1D, you can kind of manage to do it in your laptop, but it will take you to evolve a binary maybe hours or even a couple of days on your laptop. And so that means that you can probably do a set of simulations that spans, a few thousand binaries, but things get pretty expensive pretty quickly. And if you really, that means you cannot easily evaluate the impact of different assumptions, different uncertainties in stellar and binary evolution. So another approach that we've been using, along with, of course, a multitude of other groups, is let's say that we do accept that there are lots of things we don't know for sure. There are lots of uncertainties. We don't know exactly how strong the stellar winds are. We don't know exactly how big the kicks are that stars get or remnants get during supernova. We don't know exactly how efficient the common envelope ejection is. There are lots of uncertainties here. We'll parameterize them, and we want to vary those parameters and see what are the predictions for what are the models tell us under different assumptions about the parameters. And then we want to compare those to observations to learn something about the astrophysical parameters. So it's a little bit like what people may have told you about parameter estimation in analyzing gravitational wave events, except there you're looking at the parameters of an individual signal, the masses, the spins, and so on of a given binary, let's say based on the gravitational wave signal you've observed. Now we're trying to apply a similar prescription to a whole population, and now our parameters aren't the masses and spins of one given system, but they are the astrophysical parameters that govern binary evolution. And we use simple recipes to do this that are probably not quite right, but then we compensate for that by being able to do things very quickly with these simple recipes, and so we can evaluate lots of different models, lots of different assumptions, and figure out which one of those is actually the correct one. And so in our model, for instance, what we assume is that how conservative the mass transfer is depends on the relative thermal time scale of the donor and the accretor. So the thermal time scale tells you something about how well the star can stay in equilibrium. And we basically say, look, if your thermal time scale of the donor is much, much higher than the thermal time scale of the accretor cannot just accept all of the mass while staying in equilibrium. And so that's telling you that probably a significant fraction of the mass transfer will be non-conservative. A lot of the mass will just end up going into space. If the thermal time scale is comparable, then life is good and you're probably safe. And by the way, if you're asking what the thermal time scale is, the simplest prescription for the thermal time scale was actually proposed by Lord Kelvin when he tried to figure out what was the age of the sun. Has anybody heard of Lord Kelvin's thought experiment for figuring out the age of the sun? So Lord Kelvin didn't know much about nuclear fusion, and he figured, look, what's the obvious source of energy? He could tell that the sun was very bright and very luminous, right, and continued to generate a lot of energy over long time scales. So he said, look, what can power all of this? Well, the obvious answer is gravitational binding energy, right? He figured that, if the sun is contracting over time, that releases lots of binding energy. Okay, somehow you convert this binding energy into photons. Okay, that's not a crazy idea that if you can reprocess binding energy, convert it into thermal energy, and ultimately into photons, and that's what powers the sun. And he said, okay, look, we can measure the luminosity of the sun. He actually had a pretty good value for the solar luminosity. It's not that difficult to measure. So let's just ask how long the sun could continue to emit this level of energy, this luminosity, if this came from the binding energy. So all he did was he said, look, imagine that the rate of energy loss from the sun is the solar luminosity, which is you can measure. You can measure the flux from the sun. If you know the distance to the sun, you get the luminosity. The binding energy is something of order g m sun squared over r sun. And if you just say the lifetime, and today we call it the Kelvin-Helmholtz time scale, so hence the kh, is just the binding energy, gravitational binding energy, divided by the luminosity, that gives you a time scale. Now, the answer for the sun turns out to be about 1 million years if you do this. So that's actually telling you, if you happen to know for other reasons the sun probably exists for longer than 1 million years, that tells you there must be another source of energy, and you pretty quickly figure out that the source of energy, of course, is nuclear fusion. And you have a much larger reservoir of energy there, right? So if you compare g m sun squared over our sun, and you compare that to 0.001 of m sun c squared, which is something like, accounting for the mass deficit, trying to very crudely estimate the mass deficit of hydrogen when you're trying to figure out how much energy you might release if you fuse the hydrogen in the sun to helium, right? This is a much, much larger number. So that's why you can actually power the sun for 10 billion years, not just 1 million years with nuclear fusion. But this time scale, despite Kelvin being wrong in his estimate of the solar age and of the source of solar energy, the time scale is actually a reasonable time scale in the sense that it's a useful thing because it tells you roughly the time scale for the star to come into thermal equilibrium, and so it can kind of tell you and I give you an idea of how long it will take the star to come to thermal equilibrium if you transfer mass to it. You compare it to the thermal time scale of the donor and figure out how conservative the mass transfer is. So we have this, let's imagine, fairly conservative mass transfer during the first phase of the mass transfer. Let's also imagine that it's stable, meaning you don't go into a common envelope phase. Typically, if you do, that's great, except that you're not going to form a double complex object binary, because you will either have a merger during this common envelope phase, or you will find that during the subsequent expansion of the secondary, the initially less massive star, you end up going through a merger because now your two stars are far too close together. You survive the first supernova explosion. You succeed in going through a common envelope during the second episode of mass transfer and harden your binary by something like a factor of 100. And you survive this common envelope phase. You then survive a second supernova explosion, and you end up with two complex objects close enough to merge within the age of the universe. So these are roughly the conditions for you to make something like a merging binary black hole. And so you might try to ask yourself, well, how unusual is this? How rarely does this actually happen? And is this at least interesting from the kinds of arguments we were making earlier, right? We might ask ourselves, do we actually form enough binary black holes this way? Can we form enough binary black holes this way to explain, for example, their observed rates? Is this a potentially interesting channel? And I was going to cheat a little bit by looking up my notes on this just to make sure I pick reasonable numbers. So you can write down something like a Drake equation, right? So remember, Drake tried to write down this equation for how often there might be intelligent life in the universe by multiplying a whole bunch of factors that most of which he didn't know the values of, some of which we know the values of a little bit now, like we know how often there are planets around other stars and how many stars are in the universe and so on, some of which we still don't know the values of. Here we actually kind of know the values of most of these factors, more or less, and so you can write down an equation that looks something like this. So the fraction of things that make binary black holes might be something like the fraction of primaries that are in the right mass range times the fraction of secondaries which are in the right mass range times the fraction of initial separations which are in the right range times the fraction of things which survive the first supernova times the fraction of things which go through a common envelope phase and survive it, times the fraction of things which survive a second supernova, and times the fraction of binaries which end up merging within the age of the universe. So if you consider all the stars out there and you ask, well, what fraction of stars are actually going to make black holes for me, things more massive than 20 solar masses or so, you quickly find that the right fraction of something like 0.1% of all stars are by number are more massive than 20 solar masses. So this is about 0.001. Now the fraction of secondaries is surprisingly much higher than that, because remember I told you that the secondary in a binary is not picked independently from the initial mass function. It's picked according to a roughly flat distribution in the mass ratio. So actually if your primary is massive enough, something like half of your secondaries are going to be massive enough, right? If your primary is 40 solar masses, in half of the cases your secondary will be 20 solar masses or higher. So this is in fact a quantity of order 0.5. And this is very hand-wavy. I'm not doing this as a proper integration. If you want to do this as a proper integration, of course, that's where we apply tools like Compass to actually figure out the exact details of the mass distribution and the fraction of binaries that go through this channel, and how these all depend on the assumptions we make about stellar winds and so on and so forth, right? So this is just a hand-wavy approach. The initial separation, okay, so you might think that this requires a lot of fine-tuning for initial separation. Actually, it doesn't. It doesn't because your stars expand by so much during their expansion after the end of the main sequence and moving towards the giant phase. And it sort of doesn't, it's not so critical where that initial separation is, as long as you want to make sure that the binary is close enough together to interact. Okay, if your binary is so far apart, let's say your binary is 100 AU apart, it may never interact. Okay, then of course if it never interacts, it's very unlikely to ever come close enough together to make a double compact object, unless maybe you get very fortuitous supernova kicks. It's conceivable, right? If your companion is orbiting this way and it gets a kick in exactly the opposite direction and with a magnitude that is almost equal to its pre-kick velocity, right? So it basically stalls in place and then falls onto the other object, right? Yes, it's conceivable, but it's a set of order 0, right? It's very, very rare. So that's we cannot rely on that to happen. And if you can do numerical experiments and find this is extremely rare indeed. But the nice thing is that because the initial separation is distributed uniformly in the log, there is sort of the fact that you have a couple of orders of magnitude of expansion there between the main sequence and where you probably don't want your binaries to be in contact on the main sequence, and the giant phase means that out of the entire range of binary separations, which might be 4 orders of magnitude, you've got 2 orders of magnitude to play with. So this is actually something like, again, 0.5 of all binaries will interact at some point when this companion becomes a giant and then the other companion becomes a giant, and you will have possibly mass transfer going in both directions. The fraction that survive the first supernova, okay, that depends quite heavily on whether you're talking about a binary black hole or a binary neutron star. Binary black holes, we think, most likely don't get very significant kicks. There is obviously a lot of uncertainty on this, but one of the things you can look at are the current velocities, where you know them, and locations of black hole X-ray binaries. We know that massive stars are born in the galactic disk, and so if you can tell what the velocity of an X-ray binary is, right? Remember, an X-ray binary is a binary composed of a compact object like a neutron star or a black hole and a normal stellar companion. If you look at the velocity of that binary, relative to the galactic disk, or if you even look at the position of the binary, how high it managed to move up above or down below the galactic disk, it tells you something about the kick magnitude. And it in fact seems that for the black hole binaries, well, at least that's my interpretation, there's a little bit of a disagreement there in the literature. So some people, I should say, people like Serena Repeta and Heist Nellemans have argued that actually there may be evidence for some significant kicks in, let's say, black hole low mass X-ray binaries. I've reanalyzed some of the data a couple of years ago and have concluded that there is really no strong evidence for the kicks. I'm giving you my personal view, which may not, but I should also point out that there's still some ongoing debate about this. But my personal view is that there's really no evidence for black holes ever getting kicks above about 100 kilometers per second from supernova. It doesn't mean that they cannot get larger kicks. It means that there is no system that we can point to and say, yep, definitely the system had a kick above 100 kilometers per second. So given the fact that black holes have fairly small supernova kicks and probably don't lose a whole lot of mass during the explosion, both of these fractions are going to be of order unity. For neutron stars, this fraction may still be close to 1, because by the time you have the second supernova, your binary is already quite compact. But this fraction is going to be much less for double neutron stars. So if we redo the analysis for double neutron stars, this number is going to be larger, this number is going to be smaller. The overall rate is probably actually somewhat comparable, maybe slightly higher for double neutron stars, the volumetric merger rate, but not more than an order of magnitude higher. We can talk about double neutron stars later. So it's higher largely because the fraction of primaries is of course going to be larger, because we talked about this this morning, that you might have 4 or 5 times as many neutron stars as black holes in the universe. This common envelope fraction, this one is a little bit tricky, but this basically comes down to saying something like the following, that you kind of need to play around a little bit with the mass ratios, right? You want things where, and one thing that I haven't explicitly included here is that you want the first mass transfer to be conservative and stable. So that means you don't want necessarily a huge mass ratio initially, but you want enough of a mass ratio during the inverse mass transfer to have a dynamically unstable mass transfer, to have a common envelope phase so you can harden the binary, because remember initially the binary is quite wide. And to do that you need a mass ratio of something like 4 to 1 or 3 to 1 at least, otherwise it will typically be dynamically stable. And the way to do that is that initially you have to have fairly comparable masses, then you only have a fraction of the mass of the primary left behind, maybe a third of the mass of the primary actually ends up making a black hole. The mass of the secondary has grown, and if the masses initially were close to comparable, the mass of the secondary is now larger because you've transferred some mass onto it during the initial mass transfer phase. So maybe now, if this was initially, let's say, pick a number, 50 solar masses, and this is 40 solar masses. After this first episode of mass transfer, you removed most of the envelope. So this is maybe 25 solar masses. Maybe 20 solar masses get transferred into the secondary. This is 60 solar masses. You have some more winds before you go supernova, and maybe in the end you end up with a 15 solar mass black hole. This thing also, of course, has a bit of winds, but not so much before, while it still has an envelope. Most of the winds kick in after you've already lost your envelope during the Wolf-Rayet phase. So maybe this is 55 solar masses, and now, okay, you can see you have a mass ratio of 3.5 to 1 or 4 to 1, right? So this is kind of a typical picture you might get, but it requires a little bit of fine-tuning of the mass and separation, so I'm going to put this as roughly 0.1. And this is actually fairly consistent with the simulations that you do when I talk about this population census modeling. And the final question is, okay, what fraction of them actually merge? That number turns out not to be so crazy, because at first you might sort of be wonder how to even estimate this, but remember that initially we said that the same major axis distribution as P of A goes as 1 over A. If that were to remain true through all of this complicated binary evolution, then this would immediately lead to P of tau goes as 1 over tau. Why? Well, because tau is the gravitational wave merger time scale is a power law in A. It goes as A to the 4th. So as long as the merger time scale is a power law in A, then if P of A is 1 over A, P of tau is 1 over tau. But because this is such a high power, you have such a strong dependence on A, it actually turns out that even if this thing changes significantly from 1 over A, like it becomes 1 over A cubed rather than 1 over A, it doesn't matter all that much for this. The gravitational wave merger time scale always ends up being pretty close to P of tau is 1 over tau. Okay, I see people being surprised by this, so let me go through this. Okay, suppose for the sake of argument that P of A after the common envelope phase is actually not 1 over A, but it's proportional to 1 over A cubed. We've changed things. There are reasons to believe it actually stays close to 1 over A, and I can explain why. But let's suppose that we have a somewhat different distribution. Let me try to argue that it doesn't actually change P over tau all that much, right? So P of tau, remember, P of tau d tau has to be equal to P of A dA. Okay, because this is the probability density and this is the probability density, but it's tricky to work with probability densities. It's easier to work with actual probabilities. And this is a probability over a given range, so probabilities have to equal. It doesn't matter what parameterization you use. I can parameterize things in terms of x or in terms of x squared. My densities will be different, but my actual probabilities will be the same. So my actual probability of getting an x value of x between 1 and 1.1 is the same as my probability of getting x squared between 1 and 1.21, right? So I can use this to determine P of tau. P of tau is P of A times dA over d tau. I can write this as d tau over dA to the -1. If my tau goes as A to the 4th, which it does for gravitational waves, then d tau by dA is, okay, so this is, forget about the factors of 4, I don't care about them. This goes as A cubed, so this is tau over A. I plug this into here. I end up with A over tau, so this gives me, I've run out of space. This gives me P of A times A over tau. I plug in here that P of A, let's say, is 1 over A cubed. So this is 1 over A cubed A over tau. Now I remember that tau goes as A to the 4th. So this is A over A to the 7th. So this goes as 1 over A to the 6th. And again, remembering that tau is A to the 4th, this is 1 over tau to the 1.5. So, okay, if I go from 1 over P of A going as 1 over A to P of A going as 1 over A cubed, my P of tau stays pretty close to 1 over tau, right? So what this means is, okay, what does P of tau goes 1 over tau actually mean in practice? It means I have as many binaries merging with a delay time between 10 million years and 100 million years as between 100 million years and 1 billion years as between 1 billion years and 10 billion years. So that means that, in fact, as long as my minimal delay time is not too large, okay, if my minimal delay time is 100 billion years, I have no binaries that are merging, but the minimal delay time is less than the age of the universe, I will have a non-negligible fraction of binaries merging within the age of the universe because of this flat and log distribution of delay times. And if you ask yourself, well, what is the minimal delay time? It's actually pretty simple, right? the minimal delay time must be such that my secondary, after I have stripped it down to just the core, and remember the core is only a couple of solar radii, can still fit inside this binary. Okay, if it cannot fit, if it's already being disrupted by this black hole, okay, that's it. I don't get a binary black hole merger. But if it can stay in there, then all I have to do is evolve those systems forward, and they will give me the shortest delay times. And those shortest delay times are only order of 1 million years, between 1 and 10 million years, depending on whether you're thinking what mass you're thinking about. For double neutron stars, they end up about 1 million years. For double black holes, about 10 million years. So the minimal delay times are measured in the millions of years, and so that means that because of this flat and the log distribution, I get a sizable fraction of all binaries that actually will merge within the age of the universe. So I can put this, let's say, as 0.2. And so if I do that, okay, let's try to do the algebra. So 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. So I get something like 5 times 10 to the minus 6. So 5 times 10 to the minus 6 of all of my stellar binaries might make binary black holes. Well, let's remember the overall star formation rate. I said that the star formation rate is something like a couple of solar masses per year in the Milky Way, and that because the space density of Milky Ways is 1 per 100 cubic megaparsecs. That means I have something like 10 to the 7 solar masses per year forming in a cubic gigaparsec. That's actually very consistent with the overall average star formation rate at redshift 0 in the modern universe. If you look at, for example, Pierre Madao, who looks at the star formation rates as a function of redshift, as a function of the age of the universe, the numbers he quotes for redshift 0 star formation is about 0.015 solar masses per cubic megaparsec per year at redshift 0. So the modern star formation rate is about 10 to the 7 solar masses per cubic gigaparsec per year. That actually means about 10 to the 7 binaries per cubic gigaparsec per year, because the typical stellar mass is like half a solar mass. So a typical binary's mass is 1 solar mass. So if you have, and something like 2/3 of all stars are in binaries. So within my hand waving, I have about 10 to the 7 binaries per cubic forming per cubic gigaparsec per year. So if I multiply this by 10 to the 7 binaries per cubic gigaparsec per year, I get a number that is 50 per cubic gigaparsec per year. And lo and behold, that's smack in the middle of what LIGO and Virgo are telling us might be the binary black hole merger rate. You shouldn't look at this and say you're convinced that this is the right channel. I'm not convinced this is the right channel. There are plenty of uncertainties, and one of the big ones, for example, is what actually happens during the common envelope phase. Models of common envelope evolution through hydro simulations are turning out to be very, very challenging. Observations are also challenging. There are observations of plenty of binaries which we think are post-common envelope binaries, and you can only, as far as we understand, explain them as post-common envelope binaries. In fact, all the known galactic double neutron star binaries fall into the category, as well as plenty of other systems. We think there might be events that are associated with common envelope ejections. So these are so-called luminous red nova. Luminous red nova are a particular type of transient events which are brighter than a typical nova. So remember, a nova is a little deflagration on the surface of a white dwarf when you dump a little bit of mass onto a white dwarf. So you have a nova, you have a supernova, which is basically an explosion of a star with maybe something left behind in the case of a core collapse supernova, or nothing left behind in the case of a white dwarf merger in type 1a supernova. Now we know, after the recent discoveries, there are also things in between called kilonova, which are thought to be associated with double neutron star mergers. A nova is less luminous than a kilonova, more luminous than a nova, and it looks quite red in color, and it lasts for quite a while. We're talking about sort of months in duration, and there are reasons to believe that it has just the right properties to be explained by a common envelope ejection. And so this is one of the ways you might be able to constrain observationally common envelope physics, but at the moment this is a very uncertain step. Lots of big question marks. But at least if you believe the overall picture, then maybe you might trust that the overall rates I'm trying to give you here aren't completely crazy, that this could actually be responsible for a non-negligible fraction of the LIGO-Virgo events. So questions on this isolated binary evolution channel before we move to the other two channels I wanted to mention. Oh yes, so this, so I'm not providing all of the references, so if you want to look at a sort of historical list of references, actually take a look, for example, at the review that Alison Farmer and I had written earlier this year. I mentioned it in the first lecture. But people, I mean, the first mention I know of possibly merging double complex objects actually comes from two Russian guys, Tudukov and Yungilson, who wrote about this in 1973. This is really impressive. It's before the first observation of a pulsar, right? So this is really, impressive stuff. If you go a little bit, further onwards, you look at sort of papers from 1975, 1976. Bogdan Paczynski, a Polish astrophysicist, described the physics behind a common envelope and talked about this particular phase of the evolution. And in the intervening years, the Hals-Taylor pulsar was discovered. By the way, I should correct myself. When I said 1973, of course, it was after the discovery of the first pulsar. It was before the discovery of the first double complex object system. The double complex object systems were predicted. But after the discovery by Hals and Taylor of the double pulsar, or double complex objects, double neutron star binary, there were explanations of it as coming from people like Ed van den Heuvel as a post-common envelope system. And so people have been working on these kinds of predictions going back to 1970s, 1980s, 1990s, and quite actively, certainly during the period leading up to the construction of LIGO and during the operation of the first phase of the LIGO and Virgo instruments, so during the 2000s and early 2010s. And in fact, people have commented on the fact, I think slightly unfairly, that it was a great surprise that the first discovery of LIGO was a double black hole, not a double neutron star. I think it was surprising in the sense that we knew observationally of the existence of double neutron stars and not of double black holes. It's very hard to see double black holes except in gravitational waves, whereas we had known of something like 15 double neutron stars in our own galaxy. And some of them we knew, about 5 of them we knew would eventually merge, not in our human lifetime, not possible LIGO sources, but at least, if you assume other galaxies are not that different from the Milky Way, it's reasonable to assume double neutron stars will be merging elsewhere. So double neutron stars were a sort of more confident LIGO source perhaps than double black holes, but in fact there had been papers ranging from well before the LIGO observations saying that actually double black holes and fairly massive double black holes might be the most common LIGO source. So for instance, Chris Blaczynski, who will be speaking here next week, had worked on some of these things starting from the 2000s, and I think he had a paper around 2010, specifically just titled something like double black holes are the most common LIGO source. I don't remember the exact words of the title, but it was something along those lines. And we had collaborated with him on some of these predictions for over multiple years, well before the LIGO detection. So absolutely, these things were predicted, but obviously with a large grain of uncertainty, because these are predicted theoretically. You don't have direct observational evidence, of course, before the LIGO-Virgo observations. Yes, please. Oh, for double black holes, I said it's between about 10 and 200 per cubic gigaparsec per year. For double neutron stars, LIGO and Virgo claim actually what I think is an unreasonably and artificially high range. So I don't remember the numbers because I think they're unreasonable. And they're unreasonable for two reasons. But fundamentally, they're unreasonable because the LIGO and Virgo data analysts decided to ignore prior information. Actually, they decided to do something very interesting. If you look at the LIGO-Virgo paper announcing double neutron star discovery, they quote a rate, and they don't actually tell you what prior on the rate they used to compute that rate. And you might say, well, why do you care? And it actually matters a lot if you have one observation, right? So if you're a Bayesian, and the LIGO-Virgo people are Bayesians, they fundamentally compute this in Bayesian ways, but in this case, they kind of, forgot something important. They forgot to tell us something important in the paper, because if you have a lot of information, for those of you who are familiar with Bayesian analysis, your likelihood dominates and your prior doesn't matter, and your posterior is completely dominated by the likelihood. If you have very little information, like one event, and remember Poisson statistics tell you, 1 plus or minus 1 within error bars, right? Your prior is pretty important. And you can, for rates, you can pick different reasonable choices of prior. You can pick a prior that's flat on the rate, a prior that's flattened 1 over rate, a prior that's flattened 1 over square root of rate, that's Jeffrey's prior. These things give you differences in the quoted peak rate of a factor of 2, just the choice of the prior. And so it's a little bit surprising that there was no prior given the LIGO paper. Now, talking to LIGO folks, they tell me that they used a flat prior on the rate, which tends to lift up the posterior. But I think more importantly, they chose, and it's a reasonable choice, but it's not the only reasonable choice, to ignore all of the other priors we might have. Because of course, for double neutron stars, unlike double black holes, we already have plenty of information. We know something about how often double neutron stars merge in the galaxy, because we know of 15 double neutron star systems in our own galaxy. Yes? Well, yeah, so you can choose to, indeed, you can choose to take whatever prior you want to, as long as you tell us. So my only real complaint was about you not telling us, but which prior you use. So I think that's a valid complaint. But I agree that you can choose whatever prior you want to. I would say, okay, so now speaking for myself, I would say that in this particular case, you do have prior information. You know something about the double neutron stars that are emerging in the galaxy. You know something about short gamma ray bursts. I mean, now we know definitively that short gamma ray bursts. So does it say that it's flat in the paper?
It's upper limit of 12,600.
Okay, so I did not see the words flat. I definitely looked. Okay, in that case, okay, so maybe Nelson is telling me that I cannot read. Okay. Okay. All right. Well, okay. If I'm wrong, I apologize. I really did check. Maybe I just cannot read. But fair enough. Fair enough. I'm sorry. I did not mean to offend anybody or badmouth anybody. That paper has a lot more exciting information than this, and I totally understand that there were lots of things to put in there. So anyway, but I personally think that there are other priors involved, because we actually do know something about the systems. For example, we know that they are associated now with short gamma ray bursts. We know something about the rate of short gamma ray bursts and their beaming angles, so we can extract something about the rate of double neutron star emergence from those. We can extract something about the rate of double neutron star emergence from the observed galactic population. We can, if you believe anything about our models, we can, we get some prior from that as well, if you wish. And so I actually think that the rate of double neutron star mergers is going to be, in fact, something very similar, the volumetric rate, to the rate of binary black hole mergers. So I would actually guess it's going to be on the order of, let's say, 20 double neutron star mergers per million years per galaxy, which is about 200 double neutron star mergers per cubic gigaparsec per year. LIGO, the current sort of claimed rate, which by the way again, is the median, not the posterior, the peak of the posterior, so it also changes things by another factor of almost 2. But it's almost an order of magnitude larger than that, and I think that's possibly an overestimate, and you got lucky, and that's good. I mean, we should be very happy that we got lucky, but unless, let's see what the future holds. It may be that I'm completely wrong, but if I, being a betting person, my bet would be that we got a little bit lucky. We really, had only maybe a 20% probability of seeing something between the 01 and 02 run. We saw something. We got very fortunate. That's great. But okay, it also means that maybe we won't see quite the same rate of the systems during 03. So I wouldn't be totally shocked if we don't see. Okay, it depends on how the detectors improve during 03, but we may not see something more double neutron star mergers for a little while longer. Let's see. I think so my guess at the rate is that it's sort of order of 100 to 200 per cubic gigaparsec per year for double neutron star binaries, with big error bars, of course. Okay, so more. Yes, please. That is true. Well, so what I would say it slightly differently. If this is the right channel, then every binary black hole that is going to merge must at some point have looked like an X-ray binary. It does not mean that every X-ray binary will end up making a double black hole. And in fact, the majority of them won't. So for example, Cygnus X1, which is one of the best studied X-ray binaries around galaxy, I am fairly confident, and we can discuss why in more detail, that it will never make a emerging double black hole. Okay, so that's a very good point. So let's talk about the spins. So I actually think that in this that for things that go through this channel, the spins of both black holes will be almost 0. Why do I think that? I think that's true because if you consider a typical star, a giant star, and you spin it up as fast as it can go, right? I mean, there's a maximum limit. At some point, you go above the mass shedding limit, right? If you rotate it so fast that at the periphery of the star, you're moving faster than the local Keplerian velocity, right? Than the local orbital Keplerian velocity, you just shoot off mass into space. So that it gives you a maximum orbital or maximum spin velocity for the star. If you imagine the star is anything close to uniformly rotating, this is a key point. So uniform rotation means omega, the angular velocity, is the same throughout the star. Does it have to be true? No. Of course, you might imagine the core of the star is much more rapidly rotating than the outer reaches of the envelope. However, observations, and we don't have any good observations of 50 solar mass stars, but we do have observations of 2 solar mass stars through astroseismology. So for astroseismology is an attempt to look at the internal modes, internal oscillations of the star, and the stellar rotation provides a kind of a splitting in the oscillation frequencies, and so you can, it's a little bit like some kind of a Zeeman splitting in atomic spectra or whatever. And if you look at these splittings due to the frequencies, and there are different kinds of modes in the star, some modes propagating through the envelope, some modes propagating through the core. You can measure both in some cases, and it seems that for a couple of observations of 2 solar mass giants, much lower masses, but a couple of observations of 2 solar mass giants, there is very little differential rotation. The core is spinning with an angular frequency that's only a little bit faster, but not orders of magnitude faster than the envelope. Now, if that's true also for high mass stars, big if, but if it's true for high mass stars, you can compute what is the dimensional spin parameter for just the core versus the whole star. And you compute it for the whole star, and it's way above 1. For a star, remember, 1 is the maximum for a black hole, but a star can have a spin parameter far in excess of 1. Nothing prevents it, right? A star is big. It extends much, much beyond the Schwarzschild radius, and so it has this big lever arm. It has a huge moment of inertia relative to a black hole per unit mass, right? Because it has this big radius. And so a star, you don't have to spin it all that fast for it to have a dimensional spin parameter significantly in excess of unity. But all of that dimensionless spin, in fact, all the angular momentum, is in the envelope. It's out there, just because the moment of inertia is so much higher here. The core, meanwhile, has a tiny, tiny fraction of the angular momentum. And so if during binary evolution you strip off the core, you go from a chi parameter of hundreds or thousands to a chi parameter of 10 to the minus 4. The core is barely spinning. So if you manage to strip off the envelope quickly enough, for instance during common envelope phase, which can last, depending on the situation, less than 100 years, you may not have time to transfer the angular momentum back from the envelope to the core. They are essentially decoupled, and that means you, by stripping off the envelope, you remove all the angular momentum from the star. You have very little left. And so then when the star collapses, there is just very little angular momentum that it has. So it collapses into an almost non-spinning black hole. Now, of course, there are caveats to this. There are, one thing is we actually don't understand supernova explosions all that well, right, as Marian has pointed out earlier. And so, in principle, of course, it's not true that the angular momentum of the progenitor is the same as the angular momentum of the remnant. You might have, in fact, we know in some cases that the progenitor might still have an angular momentum larger than 1, chi parameter larger than 1. If it's you can have a situation where a Wolf-Rayet star has still a significant angular momentum, and one way, by the way, to do that is through tidal coupling, which I'll discuss in just a moment later. So just keep that in mind. Tidal coupling can spin you up. If you do that, this is actually proposed as one of the potential progenitors of long gamma ray bursts. So we know that some supernovae are associated with the formation of ultra-relativistic jets and long gamma ray bursts. And one of the possible explanations is that these are this relates to the collapse of a star that is rotating with a chi parameter in excess of 1. If it's trying to collapse to a black hole, you have to get rid of the angular momentum. You just cannot collapse into a black hole all of the angular momentum you have. And a jet is one possible way to get rid of the angular momentum. And so people have talked about these overly rapidly rotating Wolf-Rayet stars as one possible way of explaining where the long gamma ray bursts are coming from. But the reverse is also possible. It may be that you might have something which, a progenitor which is almost not rotating, and then you somehow eject one of your shells with a net angular momentum in one direction, and then the remnant, by conservation of angular momentum, ends up with an angular momentum in the other direction, right? So you end up creating a spin, and there have been models of neutron star explosions which suggest this might naturally happen by people like Metzacapa and Blondin and Thierry Foglizzo here in France. And so they've argued that you might generically create spin even in the absence of spin in the progenitor, but that's true for neutron stars where the spins are very low anyway. Relatively speaking, they're very low. We're talking about sort of chi parameters of order of 0.01, let's say, and if it's close enough to 0, it's not that different to change it a little bit. And we know that this, by the way, we know this happens, right? Because if you look at the double pulsar JO737, right, this is the one binary we know of in the galaxy where both companions were at least at one point observed as pulsars. Now only one, because the other one it's rotated out of the line of sight. But the fact that you had both of them be pulsars means you could measure their spin orbit alignment angles, and the secondary was misaligned by something like 135 degrees to the orbit. And meanwhile, that binary is almost circular. It has an eccentricity of less than 0.1. So that rules out a kick, right? Because, okay, one way you can get a significant misalignment is, okay, if I imagine I have this binary and everybody's happily aligned, and then I have a big supernova kick, you know, I can flip the orbit. But that couldn't have happened because that would also create a significant eccentricity. So the fact that I have an almost circular binary and the significant misalignment is telling me that almost certainly it was during the supernova that I just tilted the spin. But in this case, the secondary has a spin period of 2 seconds. So we're talking about a chi parameter of less than 1/1000th. So, okay, those kinds of things, you know, you might be able to create during supernova explosion. Maybe not so easy for binary for black holes, right? For maximum spinning black holes. So my personal view is indeed these systems, because you end up stripping off the envelope in both directions during at least this channel, you would expect that you would get nearly 0 spins for both companions, and that's actually consistent with most of the LIGO observations. Yes? So it's easy to spin up a star, and it's very hard to spin up a black hole. And again, the problem is with the black hole's very small moment of inertia. So if you ask yourself, how do I spin up a star? Well, it turns out that because most of the star's mass is fairly centrally concentrated, you put in a little bit of mass, like 1% of the mass at the equatorial plane, but moving at the local Keplerian velocity, and you've doubled the spin of the star. For a black hole, you can, you know, think of this as another homework problem. Do a very simple calculation. Imagine I'm putting in mass as fast as I can at the speed of light, right? Okay, let's do this in a purely Newtonian way. I know this doesn't quite work, but imagine the black hole was, you know, a physical object with a mass m, a radius equal to 2m in my g equals c equals 1 units, and I put in some mass, little m, with a velocity c, the velocity of the speed of light, going this way, right? That's about as fast as I can put it in. And I can ask myself, okay, how much angular momentum am I actually adding, right? Because I want, you know, suppose this thing initially was not spinning, so its initial value of chi was 0. I want to spin it up to some significant value of chi. Remember, chi is L over m squared. So suppose, for example, I put in 10% of its mass, right? So little m is equal to 0.1 times big M. Okay? So the angular momentum I'm adding is L is m r cross v. Okay, in my example, it's 0.1 m times the radius is 2m times v is the speed of light, c, which is 1. So that's 0.2 m squared. I divide by m squared. I've only spun it up to a chi of 0.2. Right? Okay, this is very naive, but it still is actually fundamentally correct in the sense that if you want to significantly, to give you a black hole significant spin, like points, you know, go from 0 to 0.7 or 0.8, you need to basically double its mass. So you need to accrete a lot of mass onto a black hole. Now, meanwhile, keep in mind the following fact. If you are accreting at the Eddington limit, and the Eddington limit is basically, okay, we can do this calculation if we have time, but the Eddington limit is basically set by the following argument. As I'm accreting, I am releasing energy. That energy that's going outwards, if it's coming out as radiation, creates a radiation pressure going outwards, and at some point, just the feedback from accretion is going to push the material out and stop the accretion. So I cannot accrete too fast, otherwise I push out all the material and stop the accretion. And if you consider this balance between accretion going inward and radiation from the energy released during the accretion going outward, this is called the Eddington limit, you find that at the Eddington limit, to double the mass of a black hole takes you about 100 million years. Meanwhile, if we're talking about these massive objects, they only live for a few million years. These stars only live for a few million years. So you cannot be accreting for 100 million years. You can only accrete for a couple million years at most. So you can never double the mass of a black hole. You can add only a small fraction of its mass, which means you cannot spin it up all that much. So in black holes with a high mass companion, which is short-lived by definition, basically their current spin is equal to their spin at birth. You cannot change the spin through accretion appreciably. That's not true for very low, for lower mass black holes. So for example, some of the black holes in low mass X-ray binaries, there are some arguments by people like Philip Podsedlovsky and Tassos Fragos that suggest that maybe some of the low mass X-ray binaries with high observed spins may have started their life as so-called intermediate mass X-ray binaries. So maybe you started as a 5 solar mass plus 5 solar mass system, 5 solar mass black hole and a 5 solar mass companion. You were here you're talking about lifetimes that are of order 100 million years or more. So you're slowly accreting that mass over time. And now you see this as a 10 solar mass black hole or 9 solar mass black hole and a 1 solar mass companion. But you have more or less double the mass of the black hole. And that's why the black hole may be rapidly spinning even if it was born with an almost zero spin. But that doesn't work for black holes with high mass companions. You just don't have enough time. The lifetime of the star is too short and the doubling time is too long, and you really do need to roughly double the mass in order to get your black hole to be rapidly spinning. More questions? Yes, please. Through this channel, you can probably get mass ratios of order 2 to 1, even 3 to 1. Very extreme mass ratios are very challenging because you have very different lifetimes for the two companions, and if the lifetimes are too different, it's kind of hard to go through this particular channel. So, in fact, most of the channels that I know of are more likely to give you sort of comparable, where by comparable I mean within no more extreme than 2 to 1 or 3 to 1 mass ratios. Some of the channels almost equal masses. This one you can get, 2 to 1 is perfectly plausible. I should also mention one more thing in terms of the masses. I said, I think either yesterday or this morning, that in the galaxy, the most massive black hole we know is about 15 solar masses. The most massive black hole we confidently know, Cygnus X1. Maybe 16 solar masses. How do we get these 30 solar mass black holes that, like the companions in GW17, GW150914? So metallicity has something to do with this, right? I mentioned this morning that if you have a very low metal fraction, then your stellar winds are very significantly reduced. So the reason we think in the galaxy, in our galaxy, we are peaking at 15 solar masses isn't because we never get massive stars born in the galaxy. If you believe the initial mass function is universal, there should sometimes be 100 solar mass stars born in our galaxy, or even 200 solar mass stars born in our galaxy. The problem is, at the high metallicity in the galaxy, they lose so much mass during their evolution that it doesn't matter what mass you start with, you never end up with a mass more than about 15 solar masses. But if you go to a low metallicity environment, and that can typically be either maybe a small dwarf galaxy, which typically has less early generation star formation. I mean, we know that even locally, the Small Magellanic Cloud, for example, has only about a fifth of the metallicity of the Milky Way, despite being only 50 kiloparsecs away, right? And there are plenty of even lower metallicity galaxies in the local universe, right? You reduce the metallicity, and you significantly damp down the stellar winds, and you end up with being able to form 30 solar mass black holes. So if you go to maybe a 20th of solar metallicity, no problem. You can get 30 solar mass, maybe even 40 solar mass black holes. You go to the metallicities of the very early universe, just after the Big Bang, population 3 stars. Okay, if it weren't for pairing instability supernova, you could in principle get 150 solar mass black holes, no problem. Because you have almost no winds at those very low metallicities. Yes. Yes, up to a point, because of course, remember that we did say that the time delay can have quite a long tail, right? I said the time delay distribution can be um, roughly flat in the log. So that means that there are sort of two different places, and it might even be a sort of bimodal distribution of where the binary black holes that are merging nearby today that we can see, things merging in a redshift of 0.1 in the local universe, where they might have formed. They might have formed either at similar redshifts, 0.1 or 0.2, with a short delay time of only 10 million years, or they might have formed at a very high redshift, meaning very early in the history of the universe, but with a very long delay time of 12 billion years. Because of course, there's a preference for the short delay times that are still, okay, it's, p of tau going as 1 over tau still gives more weight to short delay times. So that favors the short delay time version, form locally, merge after a short delay. But on the other hand, in the early universe, the star formation rate was much higher. So at redshift 2, the star formation rate was more than a factor of 10 higher than it is today. And in particular, the metallicity was much lower, so the fraction of star formation that happened at low metallicity, which is key for forming the massive binary black holes, was much, much higher. And so you may, in fact, be dominated by the tail of things that formed in the early universe, had a long delay time until merger, and are only merging today. And of course, even in a given galaxy, its metallicity isn't fixed over time. So you might look at this galaxy and you might say, oh, well, this galaxy today has, a solar metallicity. There is no way it could have formed black holes as heavy as those in GW 150914. But then you realize, well, but this galaxy, lots of the stars in this galaxy are 12 billion years old. At some point, the early generation of stars in this galaxy were born in a low metallicity environment. And you might have formed those black holes. Remember, this part of the lifetime of the star from here to here takes 3 million years. From here until merger can take 12 billion years. So you might just have a very long delay time. The galaxy today to you looks, big, red, and dead, high metallicity, elliptical galaxy, not much star formation going on at all, nothing conceivably exciting, but maybe 12 billion years ago, it had a low metallicity, lots of active star formation, it formed these guys, and then it just sat there for 12 billion years, very gradually spiraling in. So, I mean, your point is valid. This is just a caveat that you have to be a little bit concerned about this, right? And it's certainly true that, for instance, the host galaxy of the double neutron star, GW 170817, there we do know the host galaxy, unlike the binary black hole mergers, it has very little ongoing star formation. Almost, if you look, so we have a paper led by Andrew Levan, which looked closely at the properties of the host galaxy, and it basically has no star formation in the last billion years to speak of. The star formation peaked at 5 to 10 billion years ago, right? So that means that most likely this particular source formed, maybe the stars formed 5 billion years ago, and then you just had to patiently wait for 5 billion years for the two neutron stars to merge. And it's not crazy, because we look at our own galaxy and we see some double pulsars that are going to take hundreds of millions of years to merge, and in some cases that are never going to merge at all. That will merge eventually, rather, but in longer than the current age of the universe, right? They might take 50 billion years or 100 billion years to merge. Out of the 15 double neutron stars we know in the galaxy, only, I think, 6 are actually going to merge in the next 10 billion years. By the way, I didn't check when I started, so when am I supposed to stop? I can stop. I can stop now.
Start at 5:40.
10 more minutes. Okay. All right. So if there are no. Oh yes, please. Absolutely, and so that's a very good point. And in fact, you know, we have more data, for example, in short gamma ray bursts, which we are now fairly convinced are associated with double interstellar mergers, and we know that a high fraction of them, I don't remember the exact percentage, but let's say a quarter, roughly, are actually in elliptical galaxies, right? Not spirals where you expect to have relatively high rates of star formation, but elliptical galaxies where typically most of the star formation happened long ago, and there is a very low specific star formation rate. And this is telling you that, of course, you have significant delay times, and possibly some of those ellipticals are in fact merger products. You're absolutely right. I mean, there's another even bigger caveat, which is that you might ask yourself, do you actually expect ever to see an electromagnetic counterpart of a double black hole merger? We tried to think very hard about this. We even organized a Lorentz Center workshop in Amsterdam about a year ago to specifically discuss how you might get an EM counterpart of a double black hole merger. Now, of course, just at the a week or no 2 weeks before the workshop happened, GW 170817 happened, and so the workshop was partly derailed by people getting a little bit more excited about that event for very good reason. But nonetheless, after quite a bit of brainstorming, we can discuss the reasons why later, but the conclusion is it's very, very tricky to get an observable EM counterpart of a double black hole merger. So don't hold your breath. I'm not saying it's not worth checking, but it's very, very challenging to contrive a scenario where you would have a detectable transient associated with a double black hole merger. Okay, so in the 10 minutes left, I wanted to at least mention something about one more channel, which is this chemically homogeneous evolution channel, and then we'll talk about the dynamical formation and a few other things tomorrow morning. So remember this. So this was sort of the standard channel in which the stars expanded, and I said, look, what if we have a different channel where somehow magically, here's my magic wand, I say, abracadabra, stars, thou shall not expand. If I can just keep the stars from expanding, my life would be so much simpler. Because then I take two stars, put them very close to each other, almost in contact, let them happily evolve in place. They never expand. Eventually they both form black holes, and eventually they happily merge, and life is good ever after. Let's imagine that was a mustache that I failed to draw in there. Okay, so how do I do that, right? I mean, after all, I just told you that stars have a core where fusion is happening. Hydrogen gets fused into helium. They have an envelope, which is all helium. Eventually, the helium core contracts. The envelope expands, right? I gave you this very nice picture, very intuitive picture at least. I don't know if it was nice, and now I'm telling you that somehow I want to pretend that there's a magic wand that prevents stars from doing that. Well, the magic wand says the following. Well, just imagine for a moment, you could somehow have a little mixer, right? Like one of those kitchen mixers that allows you to puree your potatoes very nicely or whatever, right? If you do that, instead of having a helium core over here and a hydrogen envelope all around, you take your helium atoms out of the core and populate the envelope with them. You bring hydrogen in from the core, So you can continue fusing it, and eventually, instead of ending up in a situation like this, where you would normally have a hydrogen envelope, hydrogen-rich envelope, and a helium-rich core in the center, you end up in a situation like this, where your entire star is just made out of helium. There's no hydrogen envelope. You fused all the hydrogen, 98% of the hydrogen, by continuously bringing hydrogen into the core with your nice mixer and moving your helium back out. And this is called chemically homogeneous evolution. Okay, here chemically refers to the different species of elements, and the idea is basically that you have about the same composition throughout the stellar evolution everywhere in the star. So it's homogeneous in the sense that the ratio of helium to hydrogen is the same in the core as in the envelope. Okay, well that would be great if you could do that, but I mean, how? I mean, what's the mixer? How do I mix up the star? Actually, it turns out that remarkably, it's precisely putting the two stars together, so close together, which I want to do anyway, because if they're too far apart, then even if they did make two black holes, they would still take more than the age of the universe to merge. So I want them to be close together in this channel. It's precisely putting them close together that allows them to be very well mixed. Why? Well, consider what happens to a star when there's another star nearby. That other star is going to excite tides, right? I mean, it's like the moon going around the Earth, right? So the moon is going around, and the oceans bulge in one direction and kind of, move, down a little bit in the other direction. Okay, we all know how that works. And of course, okay, that's, a little relatively light moon, pretty far away, right? I mean, the moon is something like, 50 Earth radii away. Now imagine you put, instead of a moon 50 Earth radii away, you put something of about the same size as the Earth, only about 3 Earth radii away. That's going to excite some pretty amazing tides. Now, if you put on those very large tides, they're going to dissipate a lot of energy, all this sloshing around. And stars, of course, want to go into a configuration where you kind of minimize the energy dissipation naturally. So how do you avoid dissipating this energy? Well, suppose, for the sake of argument, I'm sort of in a binary orbiting around Nelson here, and I've enjoyed the wonderful food they cook here a little bit too much, so I've developed a little bit of a paunch, right? So if I'm moving around Nelson, and my paunch is here in front of me, and let's say I'm not rotating at all, the problem is, now my paunch, because of the tidal pull of Nelson, is sort of pointing in this direction, and when I'm sort of standing over there, it's kind of behind me, and I'm standing over here, it's in front of me, right? And it gives me indigestion, right? It's dissipating a lot of energy. Instead, if I decide I'm going to do something very clever, I'm going to rotate around my own axis at exactly the same rate as the rate at which I'm orbiting around Nelson. Now my paunch is pointing towards Nelson, now it's pointing towards Nelson, now it's pointing towards Nelson. Look, during this whole time, my stomach never moved relative to me, right? No energy dissipation. I'm happy. So this is called tidal locking. And this definitely happens. We know of plenty of systems where this happens. It happens to stars, it happens to planets. All you need to do is to be within a few radii of the companion has to be massive enough, of course, for the tidal forces to be significant, and you need to be within a few radii of the object on which tides are excited for this to happen, because otherwise the tides are too weak to lock you within a reasonable time frame. So if I get this tidal locking, what does it mean? That means my star has to go around its axis at the same rate as the rate at which I'm going around the orbit. But remember, these by construction are very close orbits. I want to take these 50 solar mass stars and put them in a 2-day or 1-day orbital period orbit, because if it's any wider than that, these two black holes will, even if they form black holes in place, they would never merge in a Hubble time. So I'm putting them into an orbit where they're almost touching already. That ensures that once I get tidal locking, I'm pretty rapidly rotating. Both stars are rapidly rotating. If they're rapidly rotating, that gives a significant temperature difference between the equator, the poles rather I should say, and the equator, right? I mean the stars they're rapidly rotating, they get very oblate, that gives you a big temperature gradient, and if you get this big temperature gradient, stellar models tell you that you end up with very efficient circulation within the star. It goes by different names: meridional circulation, Eddington sweep circulation. It depends a little bit on exactly what's the details of what's driving it. Okay, we're not going to go into the details of that given that I have 2 minutes left, but the point is this efficient circulation is what can drive the efficient mixing. And if you have this very efficient mixing, you really can convert basically the entire mass of the star from hydrogen into helium. Now, if you do that, something very interesting happens. End of the main sequence, the star just contracts. It never expands. Why would it ever expand, right? There's nothing to expand. The entire star is a helium core. It all contracts. So two useful things happen. One is the star never expands, so you never initiate mass transfer. The second useful thing that happens is you have a much higher yield in terms of how much of the mass can be converted into a black hole. Remember I said in the very first talk that typically for a typical stellar mass, you might, even if you ignore winds, you might only get something like a third of the star's mass into a black hole, because a lot of the mass just sits out there as hydrogen, never gets involved in fusion. It's in a low density envelope where the temperature is too low, the pressure is too low, you never have nuclear processes going on. Here, you can actually basically turn the entire star into a black hole, well, minus whatever you lose in winds. So you end up with a much higher black hole mass for a given stellar mass, and you end up having these two closed stars that never had to go through these complicated things which we don't quite understand, like mass transfer, common envelopes, and so on. You just end up with two black holes that are already close enough to merge in the edge of the universe. The supernova kicks don't make any difference because these things have orbital velocities of like 700 kilometers per second, and so even if you give it a 300 kilometer per second supernova kick, won't make any difference to the binary's orbit appreciably. These things are basically guaranteed to merge, with two caveats. Well, one big caveat: you actually have to get this efficient mixing and this chemically homogeneous evolution, you have to get it to work. And that's not at all obvious. There is some circumstantial evidence that this might happen in some binaries, but there is no single object that we can point to and say, yes, we know for sure that it went through chemically homogeneous evolution. When I say circumstantial evidence, there are some binaries where you look at a star and you say, look, none of our stellar models can explain it unless we appeal to chemically homogeneous evolution. But that's not the same as saying that we're absolutely confident about our chemically homogeneous evolution models. Yes, please. Oh, sorry. I mean, from this point on, it just evolves as a normal star would. So, you still fuse helium into carbon and oxygen and neon and magnesium and all the way up to iron, and you go through a normal supernova.
So is the point is you're mixing it up so I don't get this layer of hydrogen?
Exactly. You don't get this layer of hydrogen on the top. That's a big expansion. Oh, you will. I mean, once you form this, you may have a little bit of subsequent expansion. It doesn't matter anymore. Once you form this helium core, you go from a 50 solar mass or 100 solar mass star that had a radius of 25 solar radii to a 1 or 2 solar radii helium core. This thing is much more compact because you need a much higher temperature to ignite helium fusion than hydrogen fusion. And so at that point, yes, at that point the stars are decoupled. They're no longer chemically homogeneous. They're no longer necessarily tidally locked. But it doesn't matter because now they can expand all they want to. They're not going to expand enough to ever interact with each other. So of course, and anyway, if the masses are high enough, then possibly they just have a direct collapse. These things are going to have. So basically, this won't work for low mass stars. You actually need to have quite a high stellar mass and probably a low metallicity, because you don't want the low metallicity is required because you don't want the binary to widen too much due to winds. Because these things, there's actually a pretty narrow window where this will work in terms of separation. If they're too close, okay, you just merge at birth. If they're even a tiny bit too far apart, this tidal locking isn't efficient, or they take more than the age of the universe to merge after they form two black holes. So there's a very narrow window, and that window requires you to not expand too much, so low winds, so low metallicity, and it requires you to have quite high masses because high mass stars have a much higher fraction of radiation pressure support relative to other forms of support against collapse. And if you are kind of floating on a sea of photons anyway, if your mass is floating there in a sea of photons, it's easier to mix it up. Okay, this is a very hand-wavy explanation, but basically it turns out from more detailed modeling that largely for this reason that more massive stars are easier to efficiently mix. So probably this only works for kind of, GW15 09 14 type events, but wouldn't work for GW15 12 26 type events, right? It won't work for the 10 plus 10 binary black holes, but it could work for the 25 plus 25 or 30 plus 30 or 40 plus 40 solar mass binary black holes. Yes, please. Yes, so here the spin, your very good question. Here indeed you do expect a significant amount of alignment. The spins are likely to be higher. So at least pre-supernova, you expect chi values certainly in excess of about 0.2, possibly in excess of 1 for chi effective values. The question is what happens during the supernova, and also what happens during late stage winds, because winds are pretty efficient at spinning stars down. So when you have significant winds during this phase, you're no longer tidally coupled, and winds can spin you down. And so if you have efficient winds, they can remove quite a bit of the angular momentum. So that's something that it's not so clear, but at least potentially, you're absolutely right that this channel would, let's say, more naturally lead to higher spins. Oh, so you can do a similar kind of calculation. Maybe I even have it somewhere, or if not, I can do it. I can reproduce it now. That's fine. I thought I had it. I don't. All right, let me just do it by hand. Really? I could have sworn I wrote it down specifically for this. Go figure. I was trying to be well prepared and failed miserably as usual. So I'll have to now derive it on the spot. Give me just one more second. Maybe I will succeed in finding it, and it will prevent myself from being overly embarrassed by getting it wrong. Okay, so in this case, you need to worry about the primary masses and the secondary masses. So the primary mass, actually you have to have a much higher mass. So maybe this is 0.0002, because for chemical homogeneous evolution, because as I said, you really need primary stars that are sort of more than about 40 solar masses in mass for chemical homogeneous evolution to work. Secondary mass is still, same ballpark of, point few, because of this roughly flattened the mass ratio distribution. The initial separation, you might think that this would be a killer, but it actually turns out that it's probably not so much of a killer, because again, even if you have a factor of 2 in the range that you can deal with, your stars have to be between touching and a factor of 2 away from touching, otherwise they're not efficiently tidally locked. Remember that the initial separation of binary spans, let's say, let's give it 5 orders of magnitude, or for simplicity, let's give it 3 orders of magnitude, right? For initial stellar separations in binaries. So 3 orders of magnitude is a factor of 1,000. That's a factor of 2 to the 10th power. And so that means that if you distribute the initial separation uniformly in the log, that means every factor of 2 has the same 10% probability of happening. So this actually ends up being of order 0.1. Okay, and you can quibble whether it's 0.1 or 0.05, but for my estimate, it doesn't make any difference. The supernova survival is going to be 1. There is no common envelope phase, so this is just, there's no number here, right? There's no mass transfer. The merger fraction actually ends up being pretty much 1, because if they are tight enough to give you chemical homogeneous evolution, they will be close enough together to merge. The other constraint, though, that we need to put in is there's a fraction which have the right metallicity. Because, as I said, if the metallicity is too high, you lose too much mass in winds, and you are not able to merge in the well, you're not going to actually move out of chemically homogeneous solution altogether, or you move so far apart you don't merge in the edge of the universe. And probably this is again something of order 0.1 if you consider the metallicity distribution of star-forming material in the universe. And so now you end up with, okay, so this gives me 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. So maybe instead of you know, I said that before that this was converted into 50. So my yellow, where was my yellow? I've lost it. My yellow number was 50 per cubic gigaparsec per year. My orange number, which was for chemical homogeneous evolution, this becomes 10 to the minus 6. And so this becomes 10 per cubic gigaparsec per year. Again, I'm not saying this is how you really should do these calculations. I'm saying this is how you should check the results of somebody who claims they've done the calculation more carefully to make sure it's not completely insane, or at least that you've understood what the main features are. And in fact, we have done both these calculations more carefully using population synthesis models, and you get numbers in roughly this range. And so, of course, the exact numbers depend a little bit on your assumptions, or quite a bit on your assumptions, I should say. But you know, these numbers are not insane, right? So, and this is okay because I'm not claiming that chemical homogeneous evolution could be responsible for all of the LIGO-Virgo observed events, but for the most massive ones, in principle, it could be responsible. The rate is high enough for that. Okay, and we'll talk about dynamics tomorrow. Thanks.